All right, the periodic table, we are almost done discussing it. I have a few trends left. We really only talked about effective nuclear charge. And I'm also still waiting for an answer on who this is. Okay, still waiting. Please let me know who that is. Okay, so as a review, effective nuclear charge is the strength at which the nucleus pulls on a particular electron. Most of the time we're interested in the valence electron. Okay, and so you have a pull, and that pull correlates directly to the atomic radius. And so since the effective nuclear charge decreases within a group, you see an increase in atomic radius, right? It's kind of like onion layers, first quantum level, second, third, and fourth. You keep seeing an increase there, but within a period, we have an increase in effective nuclear charge, which means we're pulling the radius tighter and tighter. So we see a decrease in atomic radius. Just as a reminder, it makes sense because we are adding electrons onto the same quantum level as we are adding charges. And so those two electrons on the highest level, they don't shield each other very well. Therefore, our radius gets pulled in, and that continues. You continue adding charges and electrons until you have a full quantum level. And then let's say this is the n equal 2. So you've got 8 electrons here, 1, 2, 3, 4, 5, 6, 7, I don't know, it doesn't matter, it's full. Then when you go to the 3s, then you add a shell, so there's your onion layer, and so now you see a huge increase. And then the game begins again, you see a decrease in atomic radius. So effective nuclear charge is directly related to the atomic radius here, right? So by definition, we have atomic radius and covalent radius. It's a matter of having non-bonding metals. The trend is, of course, the same. These are the same type of metal. And so for covalent radius, obviously, we would be sharing. So it's half the distance between a joined atom. So here we have bonding, yet the trend is still the same. And then we have something called the van der Waals radii, which is interesting. It is the half the distance between non-bonding centers, right? So if we have 2O2 molecules that are in the solid or in the liquid or whatever, and so they're not bonding here, they're not overlapping at all, they will have a van der Waals distance of 1.5. And so this is used sometimes to make judgment calls about bond order, or even if there is an existing bond between two atoms. For example, if you were to make a krypton-oxygen bond, that bond distance should definitely be shorter than the combined van der Waals radii. So it needs to be shorter than half that. The distance between these centers needs to be shorter than half the van der Waals radii of krypton and krypton and oxygen added together. Here is, again, atomic radius. There's a trend here. We can clearly see how it is decreasing within a period and increasing within a group. So that again makes sense that we get smaller and smaller. And so and I don't know how good the scale here is, but look what happens once you go from argon. You just add a single electron here, how much larger your atomic radius gets once you are going to the next onion layer or quantum level. This is another interesting chart to look at. I have a better one here in a second. So you can kind of see the same trend here, but there's also, now what we have is new here, are the transition elements, which in Gen Chem 1 you don't really look at it much. You kind of wishy-washy over it, but look how it is actually decreasing and then increasing again until it pops out. So there's a better chart to look at here, right? So this is also including the D. So here we have the 3 Ds, and here we have the 4D and the 5D, and of course here we have the 4F. So that's all important to look at. Number one, you can clearly see the trend here within the group. It goes up, and then within a period it goes down. So that's a pretty good one to see. It's reoccurring here and here. But so the interesting trend here is for the transition metals, it kind of decreases and increases again until it comes up. And so the same thing is true for the 4D and the 5D. It's kind of like this well. Okay, so as you fill up half the D's, right, a single electron, and then when you pair them up, you start seeing an increase in atomic radius. The other really interesting phenomenon here is if you compare the 4D and the 5D, they're almost the same radius, and that's because there's a large increase in effective nuclear charge across the 4Fs, right? So this is where we insert the 4Fs, and so we have 14 electrons that we are adding on the same quantum level, the 4F. So you would expect that radius to be pulled in, and which causes the 4D and the 5D. In fact, they have very similar characteristics, atomic radii, not just atomic radii, electronegativities and everything. So this is referred to as the lanthanide contraction, right? That's just the effect of having those 14 additional elements between the 6s and the 5d. It causes the radius to decrease drastically, and therefore the 4d and the 5d to have very similar atomic radii. All right. Let's think about ionic radii. That's also something that we don't really look at a whole lot, especially if we were to try to put them in order. Okay, so now we're removing and adding electrons, and so clearly we understand that if you remove an electron, especially the single electron on the highest quantum level of sodium, you remove that electron, you really see a huge decrease in radius. In this case, we're going from atomic to ionic radius, so you need to be careful. This is not atomic to atomic. Right now we've removed an electron, so it drastically shrinks. And when you add electrons, you also see a huge increase in atomic radius there as well. You're filling up the quantum level of chloride here, chlorine to chloride. Here are some interesting comparisons of the atom and the ion here. This is to scale. You're also given the atomic radii here, or the radii. It's atomic on the left, ionic on the right, in picometers here, right? So you can compare that, and so take a look at group 7 here. The fluoride here, when you add it, is pretty large. Anyway, let's take a deeper dive into this and try to predict the increase or decrease, or we can list them in increase in order, of the ions of. So now we're going to do an ionic radius of the second period. So here's the second period. So we have lithium, beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, and then neon. Okay, so neon we're not going to have ions here technically anyway, but for sure we know we have lithium plus, beryllium +2, boron carbon also. So -3, -2, and -1. So for sure we have no trouble assigning charges to these elements. Now let's just hypothetically, there is probably no discrete boron +3 ion. Let's just make that boron +3, and then let's make carbon also anionic. It is, after all, a non-metal. We're not going to have a C -4, but just so we can make an argument. So how do we rank that? So first of all, we have a clear division between the cations and the anions. The anions are going to be much larger than the cations. And so instead of adding electrons across, we actually have the same number of electrons, right? So lithium, beryllium, and boron, since I made them cationic, are all going to obtain the number of electrons will be 2, 2, and 2, whereas the increase in proton we have 3, 4, and 5, right? So in fact 6, 7, 8, and 9. So that's just the number of protons. So that's the charge in the center. So we have 3 plus, 4 plus, 5 plus pulling on 2 electrons. So we do expect that increase in effective nuclear charge and decrease in radii to stay the same. But here we now have, instead of taking electrons away, we're adding. So now we have the neon electron configuration, which is 10, 10, 10, and 10. So those are going to be much larger. So if we were to go from smallest to largest, we would start with boron plus 3 is smaller than beryllium plus 2 is smaller than lithium plus, and then among the anions we would now have fluorine being, because you'll see that same trend, right? We have an increase in atomic number in the center, but they all have 10 electrons to pull on, so that's going to have an increase in effective nuclear charge. And so the next one will be fluoride, and then oxide, nitride, and then we'll call this carbide. Okay, so that is, you would have listed in increasing ionic radius the second period here. So be able to do that for any element on the period table, or a group, or a period. All right, so distinguish between atomic and ionic radii. Next one is ionization energy. Usually we look at the first ionization energy. That is the energy required to remove one electron from an atom. So again, that is, if we have an element and we go to the element plus and 1 electron, that is the ionization energy. And so that energy, again, effective nuclear charge kind of plays a role here, right? So if we're looking within the group, we have weaker and weaker effective nuclear charge, we are going to see a decrease in that ionization energy. So to ruin this, so again, this is for the first ionization energies. And then it also makes sense that within the period, just not even thinking about effective nuclear charge, just think about what you know about elements, right? You have metals, they are more likely to give up electrons. And then you have nonmetals, they're more likely to hang on to those electrons. They're more likely to become actually anionic. So for chlorine to lose an electron is going to be much more difficult than for lithium, right? So it makes sense that we would see an increase here, right? So lithium has a single electron. It can easily be removed. It has a very low ionization energy, whereas fluoride wants to have an electron. That's the opposite. So there we see this increase. That's the general trend. But we do see an interesting little discrepancy here between beryllium and boron, and then again between nitrogen and oxygen, and that's reoccurring. Okay, so that kind of looks like a pattern, and we can somewhat explain that if you look at the electronic configurations for, let's go look at that second period here. So if we look at the electronic configuration and look at, for example, lithium is 1 electron and then beryllium is 2 electrons. So that's 2 acids paired up. So these two actually switch, boron and beryllium. So it's going to be much easier to remove an electron, a single electron, from a p orbital than it is to break up the pairing energy here, right? So this is where we see that switch, beryllium and boron. So if I go back to that slide, it's always going to be between the second and the third here. So magnesium and aluminum do the same thing, because it takes more energy to break up a pair than it is a single electron. So the other one is a little bit more difficult to explain. So that's between nitrogen and fluorine here. So if I look at that, these two here. Now, and this goes back to Hund's rule, this is the best I can do. I can say spreading out the electron leads to more stability. And so if we remove this oddball here, this paired up electron, we end up with a half full shell. So nitrogen is going to be more energetically favorable with a half full shell. That leads to some stability. And so there's that other discrepancy here between nitrogen and oxygen and phosphorus and sulfur. Something to remember if you are asked to list the elements by first ionization energy. So another interesting point here is that we are really just truly looking at the first energy, not the second or the third electron. But we do know that beryllium, for example, is going to lose 2 electrons fairly easily here, right? So, but there's still, if we're looking at beryllium, there's going to be it's going to be harder. It's going to require more energy to remove an electron from the outer shell, the second electron, than it is the first one, and so that is an increase. And then of course you see the blue zigzag line. This is where we have reached the full quantum level, or we don't really want to go any further, and so the increase in energy required to remove the third electron for beryllium is really high, right? It's almost tenfold that of the second electron, right? And so you can kind of see here this huge increase, 25,000 versus 36, even for the third electron in boron here. So that's just a little side note, that those ionization enthalpies that are listed are for a single electron and not for both. So again, the trend here is ionization energy, and it's a decrease within a group, an increase within the period. That's the general trend. We have some exceptions, and so please remember those exceptions. The next one is electron affinity, and electron affinity actually is the energy released, and so sometimes you'll see these listed as positive values, and sometimes you see them as negative values, right? So that's the delta H's of that are negative because it's an exothermic effect if you're adding an electron to fluorine. Now think about it. You have sodium, it has an electron, it requires energy to remove that, and then if you add that to fluorine, you're going to get a release of energy, and so then that overall better be energetically favorable or exothermic, so that we have an overall bonding effect. So these are going to be endothermic, but it depends on how they're listed. If they're listed as energy electron affinities, EAs, they're going to have positive values. If they're listed as enthalpies, they're going to be negative values. By definition, it's the opposite of ionization enthalpy. You are adding an electron to an element to make it anionic. That we have a decrease here and an increase this way. And yeah, you know, you can somehow, there's so many exceptions here. Look, we go from to 0, then back up, and anyway, just be aware, know what the definition is of that. It's the energy released when you are adding an electron to an element, so that's more important. Here's another table. These are listed as affinities now, so EAs, so they have positive values. And finally, this is very important, it's electronegativity. It leads right into bonding polarity, whether we have an ionic or covalent bond. So it's the ability of an element to draw electron density towards it, and so we expect fluorine to be the highest. It is closest to the nucleus, so we have a high effective nuclear charge. It's only 1 away from being a noble gas, so it's really hanging on to the outer electrons very tightly, and so it also has the ability to pull electrons towards it. Stronger than that for chlorine. So it's noteworthy to see how huge of a difference that is from the second period to the third, right? We go from 4 to 3, 3.5 to 2.5, and then it really tapers off, right? So there's this big, you're inserting that second quantum level, and you're adding another electron, 7 electrons to chlorine, so you still are electronegative, but you have a shielding level there, and so then this really tapers off. So you don't want to just be aware of the trend, you also want to be aware of that huge difference here between the second and the third, and then this tapering off. If you look at phosphorus, arsenic, and antimony, they're almost identical, right? But there is 0.9 difference between nitrogen and phosphorus. So that's important. That tells us about whether we have an ionic bond or a polar bond, and what type of bond to expect. Look at this hovering, floating hydrogen here, right? So you do well kind of putting that in here between boron and carbon. Obviously, it's a nonmetal. We know that carbon-hydrogen bonds are nonpolar covalent. The difference between carbon and hydrogen is just 0.4. So anything that's less than 0.4 is nonpolar covalent. And then, of course, if you get to a difference that's higher than 2, we say this is ionic. The reality is we have something in between. There's ionic character, covalent character, and so especially when we look at inorganic bonding, we'll see that there's a lot of overlap. There's that a lot of these. I mean, to take a look at the electronegativities of the transition metals here, right? So iron is 1.8. That's so much higher than calcium, right, or sodium. So for iron, yeah, sure, we call it iron 3 chloride, but so truly, if you look at the difference between chlorine and iron, so that's just 1.2 difference in electronegativity. We say it's ionic if it's 2.0 or higher, so that's really has a high covalent character, and so that's going to be important for what's to come when we look at inorganic compounds. Look at that rhodium, osmium, 2.2. Let me just bring this up. Oh yeah, chromium, 1.6. Sometimes you'll see chromium 3 oxide named chromium trioxide, right? That would imply a covalent character. And so, or titanium tetrachloride. So you sometimes will see the covalent naming scheme inserted into some of these transition metals, and that's for a reason, because it's not clear-cut ionic necessarily. There is a high covalent character. Okay, so general trend, increase towards fluorine, meaning increase towards within the period, and a decrease in electronegativity going away from fluorine. So pretty easy. There are different scientists who have come up with a electronegativity scale. There's Linus Pauling, that's probably the one that we use the most, but then there's also Alred Rockow and the Mulliken electronegativity. The trends are the same, the values are slightly different. So the final thing I want to do before we move on to something really exciting is estimate the electronegativity based on the bond strength of elements. Okay, so there's actually a correlation between those. So we're going to use the Pauling electronegativity estimation here, which is this formula. So chi A and chi B. Chi are the electronegativities of two elements, so you have to have that difference here. And you do well if you always make the first one that of fluorine, because then we can always use in the Pauling scale that's 4.0. And then chi B can be whatever you're looking for. Let's do the example of the hydrogen. So we are going to be solving for chi H, and so we use this 0.102 delta. This vector delta is outlined here, and then so we have to actually take the square root of something twice here. So first we calculate delta, which includes the square root, and then we take the square root of delta, multiply by this fudge vector. And so I have to look up the bond distance, the heteronuclear bond distances of hydrogen and hydrogen, and fluorine, and then technically it's the other way around, because I want to make this fluorine and hydrogen, but since this is the product, it really doesn't matter. So I need to look up those values, and so for that you'll be given this table, or since you're taking your exams at home, you can easily Google those. But this table has the hydrogen-hydrogen bond strength here in kilojoules per mole. It has the fluorine-fluorine one here, 155 kilojoules per mole. And then if you look at hydrogen-fluorine, it's pretty easy to be able to read this chart here, right? You just go find hydrogen, and that's 565 kilojoules per mole. So these are written out here from the table. You'll have to obtain those, and then next we can calculate the delta factor. So that's just going to be 565 kilojoules per mole minus 436 kilojoules per mole times 155 kilojoules per mole to the 1/2 power, and for that I get 304 kilojoules per mole. I plug that into here, so let's bring up a new page here. So I'm going to have 4.0 minus KH equals 0.102 times that 304 kilojoules to the 1/2 power, and then when I solve for KH, I end up with a number of 2.22, which is what we expect. I think the chart we looked at had 2.1. I'll go back real quick. Yes, 2.1, so it's in the right ballpark. Again, this is just an estimation on these bond strength. You should be able to do that for bromine or for anything that's on this nitrogen. I've done nitrogen before, so it's not a very complicated formula. And so this brings us to the end of periodic trends, and so the next lecture will be something purely inorganic. It's called point group theory, deals with symmetry, and I truly look forward to recording that lecture.